So this is going to be, wow, we're skipping to chapter 8, section 8.2, and it's called Integration by Parts. Integration by parts. Now, some people would argue that there's really only two main techniques of integration that you should teach students. Now, chapter 8 is on integration techniques, okay? And we already worked on 8.1, although I want to come back to it today and go over some of the hard homework problems, right? What's the technique that's really talked about a lot in 8.1? Substitution, yeah, sometimes called U substitution. U substitution, I would say, is a certain rule backwards. The blank rule backwards. Thank you. The chain rule backwards, okay? Well, it turns out that integration by parts is going to be the product rule backwards. And so that's kind of how this all schemes together. So then what's the rest of chapter 8 about? Well, it's using algebra and trigonometry to do tricky kinds of substitutions and things like that. Okay? So I've taught some calculus courses where this is all you do. You show them how to do substitution, you show them how to do integration by parts, and you move on. Okay? Now you guys, we're going to spend 3 weeks on this stuff, right? Up till spring break, we're going to learn how to integrate. Exam 2 will probably be a non-calculator test, I'm thinking, because it's just, hey, you against the problem, you know? Whereas exam 1 was all these applications of integration. So we'll see how this all goes. I'm going to throw a few problems at you. Should I throw the formula? No, let's do this first. Let's write down the product rule. How do you guys write down the product rule? U prime V, you said, plus UV prime. Okay. That's kind of one side of it. This is, are you guys okay if I write d dx of what? Yeah, U times V. And I just realized this is probably a little bit too small for those in the back, right? Is that better? Okay. So this is the product rule. You can see now, guys?
Yeah.
The glare? Oh, yeah, yeah. You don't need it anymore. Yeah. So, let's see. I'm going to come up with a formula here for integration by parts. So I guess what I'm going to do here is, well, first of all, this is mixed notation, right? This is Leibniz, and this is Newton, right? The two inventors of calculus. Let's use nothing but Leibniz notation for a little bit. There's an advantage to doing this, all right? So how do you write U prime using Leibniz notation? Du dx, yeah. So this is, if you're okay with this, I'm going to write this as V times du dx plus U times dv dx, right? And this is the derivative of uv. Okay? And next I'm going to write, well, I guess what I really want to do here is I want to integrate both sides with respect to x. So let's see. On this side, I'll just put this, and I had, again, the derivative of uv. And of course, what's this going to become, this left-hand side? That's just going to become uv. Yeah, uv. Now on the right-hand side, let's see. I have the integral of, well, v times du dx dx plus I have the integral, again, this is with respect to x, of, let's see, it would be u dv dx. And so, just like on the left-hand side, how integrating undoes the derivative, right? That's kind of what, you know, Leibniz saw. He wrote these like fractions because they're undoing each other. You'll notice that we're left with a couple of integrals on the right. The dx's are gone, but what you have here is you have v du next to an integral, and you have u dv next to an integral. Okay? And so what we do with the integration by parts formula is we isolate this, the integral of u dv. And we get a formula. And the formula is the following. Let's write it here. The integral of u dv equals, well, it's uv, u times v, minus this integral, the integral of v du. And this formula is the formula that we're going to use throughout this section. So it takes a few steps to get it from the product rule to that formula, but that is really integration by parts. You might say, well, when's it used? Well, it's used anytime you have a product of functions. Okay? So let me show you an example or two. There's my formula. Oh, yeah, the hard part. Which function is which? See, the way that the formula works, one of the functions you're going to label as u. You guys are used to doing that. U is a function of x. But another function you're going to label as dv. And that's kind of interesting. And then you're going to have to figure out like which one to do. And sometimes if you do it the wrong way, it doesn't work. So I need to show you an example so you can see kind of what we're talking about here. So let's try this one. Yeah, that's a good problem. Let's integrate x times 3 to the x dx. So let's see how that looks. X times 3 to the x dx. So I know it's a product, and so I'm thinking, okay, I want to try to integrate by parts. U equals and dv equals. I'm going to write these two expressions down. Okay? And one thing you need to do is you need to make sure you account for everything in the integral. So blindly, you might say, okay, let's let u equal x. Okay. That's a good choice, by the way. That's a good one. And we'll let dv equal 3 to the x. Oh, dx. Always put the dx with dv. What you're actually writing here is a differential equation. Okay, that's what you're doing. So we're going to write u equals x and dv equals 3 to the x dx. Okay, next, we need to write two more things down. Because if you look at this formula, not only does it have a u in it, but it has a v in it. And not only does it have a dv in it, but it ends up having a du in it. So right away, I'm going to compute du. Now when I say I'm computing du, I'm going to write a step down here that almost no one ever does, okay? In between here, you might say, okay, what is du dx? Well, that's easy. If u is equal to x, what's du dx? The derivative of u with respect to x equals, thank you, 1. Okay, so we almost never write that, but if you did, then what you would do is you would do this move called separating the variables. You take the dx and you kind of bring it up to this. It's almost like multiplying, right? But what we're going to write is we're going to write du equals dx. 1 dx if you want. Okay? So you take the derivative to get that, and this is what kills Calc 2 students when they're first learning, is over on this side, you take the integral. You have to write down what v is. The antiderivative of 3, boy, I don't know if you guys know that offhand. Do you guys know? Well, how about this? Do you know the derivative of 3 to the x? Yeah, good Calc 1 teacher. 3 to the x times the natural log of 3. Okay? Well, it turns out if you integrate 3 to the x dx, you get 3 to the x times 1 over the natural log of 3. That's what it equals. There's this fudge factor. I hope you guys remember that. There was this constant you had to multiply by. By the way, what if it said e to the x dx? Then what would v be? E to the x, and you don't need to multiply by anything because natural log of e is... Because natural log of e is 1. Thank you. Yeah. Guys, here's my price for going from chapter 6 to chapter 8. Chapter 7 is all about exponential functions and logs, and so I have to tap into that a little bit. There's a reason I picked the examples I do. All right, you ready? Yeah, we're ready. Let's go, Paul. All right, let's do it. So let's use that formula here. Okay. And so since this formula is true, we can write down the integral of x, 3 to the x dx. By the way, you would have no idea how to do this before I gave you this formula. I'm just pointing that out. Equals. According to the formula, it equals u times v. So that's x times 3 to the x minus the integral of v du. I'm going to write this as 1 over ln 3, because that's just a constant, right? Times 3 to the x dx. Make sense? Did that help at all? I mean, now the expression is longer than it was before. Let's pull the constant out. Integral 3 to the x dx. See, the hope is that, it's funny, you start with an integral u dv that you don't know how to do. But the hope is that if you apply this formula, you get an integral that you do know how to do. And do you guys know how to do integral of 3 to the x dx? Well, now you do, right? I just did it like a second ago, right? So what do we get? We get x times 3 to the x minus 1 over the natural log of 3 times, now what is this integral? Integral of 3 to the x dx is 1 over natural log of 3, 3 to the x, right? Plus c. So there's an answer. Can I simplify? I guess I could write, well, yeah. You know, one thing you could do, I don't know if we would do this. Maybe we would factor out the 3 to the x that's common here and here, times, and I guess we have x minus 1 over natural log of 3 squared plus c, something like that. So it's 3 to the x times both of those things. I don't know. I would take either form of the answer, of course. Something like that. So kind of interesting. So you've seen an example. Questions so far? Let's try it again. What other problem did I pick out for you? Boom. Two problems to try. All right, let's write those down. So we're going to use, well, x times cosecant squared of x dx. And we're going to do then x to the third power times e to the x dx. And maybe what I'll do right here at the top before we start, let's write down the formula again. Do you guys have it memorized yet? Integral of u dv is equal to u times v. Yeah, minus integral of v du. Okay, so there's the formula that we want to use all weekend. You guys will have a lot of fun with this, right? Okay, so let's look at the two problems. Let's look at the first problem here. Now again, there's two functions. There's x and there's cosecant squared of x. You have to figure out which one do you want to call u and which one do you want to call dv. And I'd like you to talk to someone next to you about that while I pause the recording. So more than one person said, hey, let's set u equal to x. And if you do that, then dv is equal to cosecant squared x dx. You want to write all that out, right? Why did you guys choose that instead of the other way?
That's how we did it before.
Yeah, because it was on the left. So it goes on the left. Okay, any better reason? Think about it this way. What am I going to do with u? I'm about to do what to it? Take the derivative, right? I know the derivative of x. Actually, I know the antiderivative of x also. That's not bad. What about cosecant squared of x? If you try to take the derivative of it, you need to use like bing, bing, bong kind of chain rule stuff, right? What about an antiderivative? Do you guys know the antiderivative of cosecant squared? Yeah, negative cotangent x, that's right. So v is going to be negative cotangent x, because the derivative of tangent is secant squared, and so that one's that. How about du then? I write down du equals dx, and now we just apply the formula, right? So, back to my problem here. X times cosecant squared x equals u times v. So look at this. You have a u up here and you have a v down here. So I'm going to write negative x times the cotangent of x. That's interesting. Then I write, from the formula, there's a minus sign. Don't forget that. Minus integral of what? Well, yeah, there's this v du, so I'm going to write negative cotangent x dx. See, there's a minus from the formula, there's a minus from the integral. So I'll bring that negative sign out when I integrate, right? So you can see this only works if you actually know how to do the next integral. Negative x cotangent x plus, do you guys know how to integrate cotangent? The derivative is negative cosecant squared. I asked, do you know how to integrate it? There's a trick. How do you write cotangent x? What does it equal? Yeah, let's write it that way. Let's write it as cosine of x over sine of x dx. Maybe that'll be enough of a hint. Do you guys know how to integrate that now? I have to go over 8.1 a little more, I see. There's a substitution we can do. U equals sine of x, let's try that. So if we let u, so for this guy, let's let u equals sine of x, and then what does du equal? Well, isn't that convenient? Cosine of x dx. It's sitting right there, right? So really, what are you doing? You're integrating what? I guess it's du over u, or you could write 1 over u du, right? And how does that work? What does that become? Again, we skipped chapter 7, but the answer is natural log of, yeah, the absolute value of u, right? Plus c, right? So the final answer, after all this kind of section 8.1 stuff goes in, the final answer to this first problem is going to be, let's see, negative x cotangent x plus the natural log of what? The absolute value of sine of x. You need the absolute value because sine could be negative. Plus, and then it wouldn't be defined. Plus c. Check that out. Okay. We're learning integration by parts. Questions so far? You guys are going to love this next one. Here we go. I want to integrate x cubed e to the x dx. So I ask the same question. I say, would I rather have u equal x cubed, or would I rather have u equal e to the x? You're right. I don't know. Good intuition. I'm going to let u equal x cubed. And dv is e to the x dx. And of course, that's a really nice one to have, because then what does v equal, guys? E to the x. Right? Okay, what does du equal? 3x squared dx. Okay? So far, so good. So we get this is equal to, well, uv would be x cubed times e to the x minus what? Well, I could say 3, because when I'm integrating v du, the 3 is a constant. I'll pull that out in front of the integral. 3 times the integral of what? Well, I guess it would be x squared e to the x dx. And the question is that integral any better than the one before it?
Do it again, Paul.
Do it again. Josh sees an end in sight, right? He wants to do parts here. He says, let's let u equal x squared this time, and let's let dv equal e to the x dx, just like we did before. Du is equal to what? 2x dx. And then v is equal to e to the x. Yeah, this is beautiful, beautiful stuff, right? So let's see where we're at. We have x cubed e to the x minus 3. And then what I'm going to do, guys, I'm going to put a big parentheses because I'm applying the parts formula a second time. And whatever I put, it all has to get multiplied by the 3 I pulled out, right? So let's write down what goes in there. What would go in there? X squared e to the x, yep. Minus 2 times another integral, x e to the x dx. Can we integrate that one? But the end is in sight. I can see it, right? I need another color? I guess so. So to integrate this guy here, we're going to integrate by parts one last time. We're going to let u equal something and dv, right? U is going to equal x. Do you see the end in sight? Because if u equals x, what does dv equal? What is dv going to? Oh yeah, du is going to equal dx. dv is equal to, I guess, e to the x dx. And so v is just e to the x. Wow, we're getting there. Now, this is really kind of ugly, so I have some extra room down here below. I'm going to try and take advantage of that. Okay, so moving down, let's see what it looks like. We have this whole mess equals x cubed e to the x minus 3 times a bunch of stuff. And the stuff, which I started writing in black, is x squared e to the x minus 2. And now I need another parenthesis for the new integral. Check that out. That's pretty cool. So what goes in there? X times e to the x, yep. Minus integral e to the x dx. Can we do that integral? Yes, finally. So let's try to wrap this problem up now. Let's see. You guys got that far. So I guess I'll work inside out, kind of. Let's see. We have x cubed e to the x minus 3 times a bunch of stuff. And this was x squared e to the x. And I think what I'm going to do, guys, I'm going to distribute the negative 2 right now. I'm going to distribute it, okay? So I get minus 2x e to the x, but I also get plus 2 what? 2e to the x, right? And at this point, guys, I need to write a plus c also because there is no more integral sign, and so you need the plus c. You don't write plus c every time because all the constants just add up to one big constant. All right, so let's simplify. Well, I guess the only thing left to do is just distribute the negative 3. So we get x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x, right? And then plus c. So that answer is acceptable. I think Bob would probably write this, e to the x times x cubed minus 3x squared plus 6x minus 6. So if you want to be like Bob, probably write it that way. But either way is okay. It's good? Any questions so far? It's a long problem. Yeah. You want to learn this stuff, you got to learn it. Actually, there are shortcuts for this kind of a problem. There's something called tabular integration. I don't teach it. It just takes forever to teach. I mean, if you had to do this often, there might be a reason to do it. But with today's computers and stuff, I just find, okay, no, it exists. It's kind of a slick way if you have to integrate by parts over and over again. It's a way of keeping track of things. They used to teach us when we were human calculators. Joe, you had a question?
Yeah, flip back to the first one with x3
Yeah. x3 to the x dx.
I noticed something different, and maybe I'm just being crazy, but like in the first term,
Yeah.
so it's like x3 to the x. We did that differently in the one with the cosecant cotangent.
Oh, there's a mistake. We didn't catch this the first time, but it's because it was new to you. Look, I kept thinking the answer is something funny about it, but let me show you what the mistake is. Look, when you do u times v, right, it's x3 to the x, but it's also times 1 over natural log of 3, right? Is that what you're talking about?
Yeah, because I noticed that we used the antiderivative. We didn't do that
Yeah. No, you're supposed to use u and v. So I have a mistake. If you guys want to correct your notes, you can kind of follow with me. That 1 over natural log of 3 is part of the original, and so that means, yeah, you could factor that out, and this would only be to the first power, I guess, at that point. Yeah, sorry about that. The answer is 1 over natural log of 3 times 3 to the x times x minus 1 over ln of 3 plus c. Well, these things happen. Joe, thanks for pointing that out. All right, moving on. Let's get a couple problems. Well, this one. We'll just do this one. This is unique. We're going to integrate the natural log of t squared dt and again, the hardest part is knowing what to let u equal and what to let dv equal. See, natural log is an interesting function because, well, what do you guys know about natural log from calculus class? So you know what it looks like, right? I mean, that's one thing. What else? Do you guys know how to take the derivative or the antiderivative of natural log? Which one? What is the derivative of the natural log? Yeah, so if it's the natural log of t, it would be 1 over t, right? So sometimes the way you make your choice is you say, well, I know how to take the derivative, but I don't know how to take the antiderivative. I mean, you might be tempted to say, well, let's let u equal the natural log of t, and maybe I'll also let dv equal the natural log of t, but you don't know how to do the antiderivative yet. You'll learn it. I think it's an example in the book, actually. But what I'm going to do here is I'm going to take u to equal the natural log of t squared. The whole thing? Yeah, sometimes you do that, and what you do is you just let dv equal, well, really it equals 1, but I'm going to write down dv equals dt. Because remember, you always put the dt with the dv. Okay? So what does v equal now, guys? T. And now to do du, well, I use the chain rule here, the power rule, really. Bing, bing, bong. Bing, I write the 2 down. Bing, I have the natural log of t to the first power. And then bong, I multiply by 1 over t, because that's the derivative of natural log of t. So you get this big, long expression for du. Okay? So here I go. So we're going to write this problem as uv, so that's t times the natural log of t squared minus the integral of v du. Okay, what happens when you write down the integral of v du? Well, you get a 2, I'll bring that out front, times the integral of what? Just natural log of t. Yeah, the 1 over t cancels with the t there. So it's just the natural log of t dt. Now remember I said you don't know how to do this, but you do. There's a hint. I mean, I kind of showed it now. You're going to integrate by parts. Again, we're going to let u equal something, and we're going to let dv equal something. What do you let u equal? Natural log of t, because I know how to take its derivative. What's dv going to equal? Dt. When I do that, V is equal to t, and du becomes what? 1 over t dt. Okay? All right. So here I go. I get t times the natural log of t squared minus 2 of somethings. So what goes in the parentheses? So we have natural log of t times t. I'll write it as t times natural log of t. Yep, that's my uv. Minus, oh, look what the integral happens. What's the integral going to be? Just dt, because the t and the 1 over t cancel just like last time. Okay, so this is kind of a 2-step problem instead of a 3-step problem, but we get there. And so the final answer, we could write t times the natural log of t quantity squared minus 2t natural log of t, and then what? Yeah, well, what happens when you take the antiderivative of dt? You get t, and there was a minus here that I distribute to the minus there, so I'm going to write plus t plus c. Plus 2t, thank you. 2t plus c. Thank you. There we go. Okay. What do you think? Getting the hang of it, guys? I mean, I guess you find out this weekend, huh? Is this my last one? Yeah, it's my last one. Last example, and I think we'll turn you loose on the homework. So you might say, well, what does this one have to do with integration by parts? But it's all about how you think of it. So, I love this example, actually. It's one of my favorites. It's one of my favorite things in Calc 2 to teach, is this kind of example. All right, so first thing is, how am I going to rewrite it?
Maybe x times
1 over sine?
Is that the opposite?
Oh, sine times 1 over e to the x. You could. See, it's a quotient, right? But I think of integration by parts being used for products. But you can write it as a product. Do you know how? Write it as e to the negative x times the sine of 2x dx, okay? And now we're ready to try and integrate by parts. I guess we have to figure out what to let u equal and what to let dv equal. Any thoughts? I'll give you a hint. It doesn't matter. E to the negative x. All right, let's do that. U is e to the negative x. dv then is the sine of 2x dx. Okay, du is negative e to the negative x dx. And what's v? Ah. Do you know what v is? Negative 1/2 cosine of 2x. Let me check that. If I take the derivative of cosine, I get negative sine. So that's why the negative's there. Why is the 1/2 there?
2.
The chain rule, yeah, the 2. Yeah. All right, so I guess I'm ready. Let me write down what this equals using the formula. This equals negative 1/2 e to the negative x cosine of 2x, right? Let's see. Then what? Minus, oh, but wait a minute. This is really tricky, right? you have minus, 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 which means minus. Okay, just want to be sure. So minus what? How about I write 1/2, because that's a constant, and then put the integral symbol? You guys okay with that? And what are we integrating over here this time? Do you see it? Yeah, let's write the e first. Let's write e to the negative x cosine of 2x dx, right? That's what I need to integrate. Are we any better off? I don't know. Well, as Josh would say, do it again. Here we go. Let's let u equal e to the negative x. Let's let dv equal what? Cosine 2x dx. So then du is very similar, negative e to the negative x dx. I'm running out of room. I'm going to write v down here. V would be, okay, what happens when you integrate cosine of 2x dx? 1/2 sine of 2x. So let's see what happens. We get equals negative 1/2 e to the negative x cosine of 2x minus 1/2. And then in here, I'm going to write down the stuff that we get from that red substitution. So let's see, when we do uv, we get 1/2 e to the negative x sine of 2x. Right? Minus, okay, now careful here. We have minus, and then it's an integral, negative 1/2 integral of what? E to the negative x sine of 2x dx. What do you think? Yeah. I think the first time someone did this, they must have been extremely frustrated. And then somebody had a stroke of genius. This is like Minnesota Vikings in the semifinal. Like where you snatch victory from what seems like defeat. I would love to know what it was like for the person that figured this out. That we won. It seems like we lost, right? Because wait a minute. The original integral was what? This, right? The original integral, here, see this red line? Back on this side, let me write the original integral. What's the original integral? E to the negative x sine of 2x dx, right? So, if you'll bear with me, what we have right now is we have, because I have to do an awful lot of distributing here, right? This is really ugly. All right, so let's write that down. Let's write e to the negative x sine of 2x dx equals, and let's start writing down what this stuff actually equals. It's negative 1/2 e to the negative x cosine of 2x, right? And then it's minus 1/4, right? E to the negative x sine of 2x. Okay, now I have to be really careful. I'm seeing a negative 1/2 that I'm distributing here. I have another negative, and then I have another negative 1/2. So if I'm right, that's minus 1/4 of And I'm going to write it in black again because that's what was on the left-hand side. E to the negative x sine of 2x dx. Yeah? Guys with me? Now this is really cool. We're going to add 1/4 e to the negative x sine of 2x dx to both sides of the equation. It's like good old high school algebra class. Add it to both sides of the equation and see what happens. Bam. So on the right-hand side, the black is gone. I just have, let's see, negative 1/2 e to the negative x cosine of 2x minus 1/4 e to the negative x sine of 2x. That's what I have on the right. What do I have on the left-hand side of the equal sign? Five-fourths of the integral that I was interested in. I think this is so cool. So you have this equation. And so if you want the integral e to the negative x sine of 2x dx, you can get it. All you have to do is take the equation you just had and multiply each side by what? 4/5. That does it. Make sense? I think that's so cool. I mean, when you got here, you thought, we'll never make it. We're done. It's just going to keep. But you did make it. And so we get, as our final answer, here I'll write it down. Let's see, 4/5 times this stuff would be, I guess it would be negative 2/5 e to the negative x cosine of 2x, right? Minus 1/5 e to the negative x sine of 2x. And actually at this point I should put my plus c. That's a beautiful, beautiful problem.